Institute of Engineering and Technology.
Hello students, after defining partial derivative for function of two variables and defining different rules for partial derivative, like how to find total derivative for the function, how to find chain rule for the function of two variables, and how to define implicit function. Now we are going to move for the next part or the next session of this chapter, which is applications of partial derivative. In this talk, we are going to define four major properties of applications of partial derivative. The first one is gradient, second one is directional derivative, third part is the most important part for this chapter, which is tangent plane, and finally we'll see how to define normal line. So let us start with our first part, which is gradient. So if you look carefully, or if you want to define the gradient for the function f of xy at point P, which is given at P x0 y0, then it is defined by this vector quantity del f by del x at point P into I plus del f by del y at point P into j, and it is particularly defined by this notation reverse triangle into f at point P, and this reverse triangle notation is particularly known as nebula or delta. This is how we are defining gradient for any function f of xy at point P. This notation is particularly read as grade of f or del of f. The notation of this reverse triangle itself is known as del or nebula. You should note down this definition, as it is going to help you a lot in this chapter of partial derivatives application. So now moving to the graphical interpretation of this particular section, that how actually we can construct the idea of gradient for the function of two variables. So to understand this, I am taking a surface which is defined by 1 minus in bracket x square plus y square. So you can look clearly on this surface. We have different possibilities of input. To go through any random point on the surface, let us consider different inputs on the surface. So if I fix a point which is given by blue point on the surface, and if I find its gradient, then it is given by this black vector coming outside from the point radially and which is perpendicular to the surface. Now to observe this vector at this point, let us consider different point of view on the surface by rotating the whole structure randomly. And in the similar way, for any random point on the surface, I can find vector which is given by this black line passing through the point and perpendicular to the surface. So this is the whole idea of gradient for the function which is defined by f of xy. Now let us move to the second part, which is how it is application of gradient. As I told you clearly that it indicates a vector which is perpendicular to the surface and passing through the point, so it will give you a normal to the surface at point, and it is given by gradient of f at P. If you divide by its own magnitude, it will give you a vector which is of unit length, so it is known as unit surface normal. There is a particular application of this handicap throughout vector calculus also. So now let us consider one example to understand the whole idea of gradient. If I consider a surface cos x plus sin y, and if I fix the point in the domain given by P, pi, pi, how I can find its gradient? So the ingredient for the gradients are partial derivative of function with respect to x, with respect to y. I am taking input of the point P, pi. So it will give me final value of gradient at this point by minus j. Now if I want to find the unit surface normal, I should take its magnitude, and by taking its magnitude and dividing the given vector by this magnitude value, it will result into minus j. This is how I can find the unit surface normal for any random surface at any random point P. So this is the idea of gradient at any point P. This is the surface cos x plus sin y. In domain I am taking point P, pi, pi. So its location on the surface is given by this blue dot, and then the vector which we already defined or we derived at the solution of our previous question, it is given by this black vector. So this is our first chapter of this discussion, which was gradient. Now let us move to the second part, which is directional derivative. Now how to consider this whole concept of directional derivative is like this. We already know how to find partial derivative for function with order 1, but the restriction is in del f by del x we are moving parallel to x-axis only, and in del f by del y we are moving parallel to y-axis only. This restricts ourselves to move in any random direction, whereas we know in function of two variable we can approach the point, we can move towards the point in any random direction. So the obvious question will be how to define direction, or how to define the derivative in any random direction. So we are going to look at that particular part, how to define derivative in any random direction. So it is known as directional derivative. So to understand the whole idea, I am taking a sphere x square plus y square plus z square equal to 5. I am chopping it in such a way that I can look only at the upper part of this sphere. So I am focusing on positive z side. And then to fix the direction of vector u, what I will do, I will take a plane which will cut this sphere in a particular part. So after chopping a sphere with the plane, the section of plane and sphere will give me the direction in which the point is moving to find the directional derivative. Now I am fixing a point in the domain by this black dot, and then considering its image on the surface, which is given by again this black dot on the surface, and then I am taking a direction of movement which is given by this vector u, and it is defined by this yellow direction. Now a point is moving in that direction in domain, and parallelly point is moving on surface by this blue dot. So the whole calculation now is how to define this movement from black dot to blue dot in a particular direction, which is given by u cap. And therefore I am defining a displacement element or the arc length with this parameter s. Now if you look carefully, a point, blue point, which is near to the point which is defined by black point, it is somewhere very much close into the neighborhood of this input. So actually you can find a tangent line passing through these 2 points also using our regular calculation. And to define this value of directional derivative, our whole idea is to reduce this value of arc length parameter s. So if I move from blue point to black point, the value of arc length parameter s will reduce. So ultimately I want to define this derivative with help of limit. So if I fix point P with coordinates x0, y0 in domain, if I select its image by f of x0, y0, and if I take a displacement or the movement in this direction u cap, then the resulting value is Px0 plus Su1, y0 plus Su2, and correspondingly the point is f of x0 plus Su1, y0 plus Su2, and then our focus will be on this difference. If we make this difference to be 0, my blue point will come very much closer to point which is denoted by black point. This is how we are defining directional derivative. So now we are at the point where we can define directional derivative. So I am fixing a function f of xy, point p0, x0, y0, and direction u cap as ui plus uj. So if you look carefully, in numerator I have taken the difference and I am dividing it by s. So the triangular value is ultimately considered over here. So the whole concept is remaining same. Here I am finding only that value of change in a random direction u cap. And if I take s tending to 0, it gives me the value of directional derivative, which is denoted by duf at point p0 in direction u. This should be noted down. This is the first way of defining directional derivative. Now let us consider another way of defining directional derivative, much familiar way, in form of gradient. If I fix that line in a parametric form as x equal to x0 plus su1, y equal to y0 plus su2. And if I take the arc length parameter s, which is increasing in the direction of u, then by chain rule, now I can define function f in terms of s. Now why this is happening here at this particular point, function f is depending on two parameters x and y, and as we know the values of u1, u2 and x0, y0, the only change happening in xy is in terms of s. So ultimately the branch diagram will be this: f depending on xy, xy depending on s, and then know how to find the chain rule for this. So now the value of dx by ds is equal to u1. Here I am taking x equal to x0 plus su1 and y equal to y0 plus su2. And then separating these two with help of fundamental directional unit vectors I and j, it will give me a dot product of two known vectors, gradient of f at p0 into u cap. Remember here u cap is a unit vector along the given direction, and by default I am assuming that the u given over here direction is a unit vector. If it is not, then find the unit vector in the same direction and then you can find this value of directional derivative. So this is another form of directional derivative with help of dot product. Now let us consider one example to understand the whole idea. If I consider function x square plus xy, then at point 1, 2 and in direction of u I plus j, let me take first possible method with help of limit. So I need three values. I need function which is x square plus y square, I need value of x0, y0, by given point it is 1, 2, and I need a unit vector in the given direction. Now here the given direction is not in form of unit vector, so I am finding unit vector in given direction by dividing direction by its own magnitude. So it will give me 1 over root 2i plus 1 over root 2j. Taking all these values into limit and simplifying it, ultimately it will give me final answer 5 over root 2. This is how you can find the value of directional derivative. Now let us consider another method to find the same solution. Now I will focus on the method which is defined with help of gradient of the function. So for that I need to find gradient of the function, and in dot product I will take unit vector along the given direction. So for gradient of the function I am taking x square plus xy, differentiating it partially with respect to x, so it will give me 2x plus x, and then replacing x and y with 1 and 2, so it will give me 4i plus j. And again you can see here the answer is 5 by root 2. So you can select any one method from these two to find directional derivative. Now what are the properties of directional derivative? If you look carefully with the help of a second definition, the directional derivative is ultimately dot product of these two vectors, gradient of f and given direction u cap. Now if I find the angle in between these two and define it with help of theta, then with help of this definition it will give me mode of gradient of f mode of u cap into cos theta. Now as u cap is a unit vector, the final value is gradient of f at p0 into cos theta. So now as gradient of f is a fixed quantity for any function at point p0, it is a scalar quantity right now. So everything is depending upon cos theta. So now if the value of theta will change, the value of directional derivative will also change. So now depending on the range of the cos function, we can see how the variation of directional derivative is taking place. So the first possible case is, so if I consider a direction theta equal to 0, then function f of xy will increase most rapidly in this direction. Why? Because cos theta will be equal to 1, and that means value of directional derivative is maximum. So this is how we are defining most rapid increase of the function, and exactly in the opposite direction there will be the most decrease of the function. So for the most rapid growth of the function or the most rapid increase of the function, we are taking theta equal to 0, and for most rapid decrease of the function we are taking theta equal to pi, so cos theta will be minus 1. So this is value of minimum possible directional derivative. And in between these two transitions from theta equal to 0 to theta equal to pi, there will be a point where theta is equal to pi by 2, and at that point cos theta is 0. So that is the direction in which we will get 0 change into the function. So it is known as direction of 0 change. So you should remember these three: most rapid increase, most rapid decrease, and direction of zero change. Now to understand this, let us consider one illustration for this three properties of directional derivative. So in this case, I am considering a surface with a structure like this. You should look at the structure of this particular surface, and later on what we'll do, our idea is to take a point on the surface to find its direction of rapid increase, direction of rapid decrease, and direction of zero change. So at this point, what I'll do, I will fix my point of view on this surface. I will start taking its directional derivative for different directions. Here the direction is given by red line and the value of directional derivative is given by black tangent, which is passing through the point on the surface. So you should observe this structure right now. On this structure I fixed a point, and then this is the direction, a blue vector. It gives me the gradient of function, that means the direction of maximum rate of change. Now what I'll do, the green vector over here, it defines the random direction in which I am finding directional derivative. Now if you fix a point and direction which is given by this red vector, then you can see clearly this is the direction as it is matching with that blue vector previously I defined. It gives you the maximum rate of change. Now moving from maximum, in between somewhere, whenever this green vector is perpendicular to this red vector, you will see the direction of zero change, as the vector is exactly perpendicular to the growth of the function. And then if I move in the exact opposite direction of this red vector, then I can see clearly that it will give you the direction of maximum decrease. So this is the whole idea of directional derivative. Now let us move to the third part of our discussion, which is the most important part, which will help you to develop many concepts in partial derivative later on, which is tangent plane. Again, to understand tangent plane, let us consider one example. Here I am taking a simple function x square plus y square. I am fixing a point on this surface, and to understand what is happening at this point in form of tangent plane, what I will do, I will take a directional derivative. So red line indicates the direction in the domain, and green line, it randomly moves on the plane. So you can see clearly all these black lines passing through this point, it gives tangent line on the point on the surface. Combining all this will give you a plane passing through the point on the surface, which is our tangent plane. But practically it is impossible to consider this method. So what we'll do, we'll construct it algebraically. And for that I am taking a random point which is denoted by red in the same domain of the point blue. And then I am taking a vector which is passing through these 2 points. And if I find a direction which is perpendicular to this surface and passing through this blue point, then dot product of these 2 vectors equal to 0 will give me a tangent plane. This is how we are going to construct tangent plane. So for that I am taking point P0 on the surface, I am taking its neighboring point with P, I am finding a tangent vector passing through this 2 and a normal vector which is perpendicular to the surface. Now let us consider our definition. So it is n cap into a vector passing through P and P0. So I am taking n cap with help of gradient of the function, and I am defining point P0 with help of this thing, x minus x0i, y minus y0j, z minus z0k, and by taking its dot product it gives me a value of plane which is passing through this point on the surface, and it is always in such a way that any vector on this plane is always perpendicular to this brown vector, which is nothing but the normal to the surface. Now let us consider our last part, which is normal line. Now I want to find a normal line at point P0 in direction of n cap. So what I will do, I will define it with help of this direction cosines for n cap. And for that reason, what I will do, I will construct the line which is in a parametric form and which is given by parameter t. passing through point P0 and with direction cosines of n cap. So it is x0 plus f sub x P0 at t, similarly for y and for z. Now let us consider the whole idea of these two properties, tangent plane and normal line. So suppose I take circular paraboloid and I fix the point 1, 2, 4 for this parabola at x square plus y square plus z minus 9 equal to 0. How to find tangent plane and normal line? So for that I need gradient of f at point P0. So I will find its value. It will give me 2i plus 4j plus k. The definition of tangent plane is, by this take all inputs into this definition. Finally it will give you the value 2x plus 4y plus z equal to 40. So this is the value of that plane which is on the surface at point 1, 2, 4. And the normal line is given by this form: x equal to 1 plus 2t, y equal to 2 plus 4t and z equal to 4 plus t. You should pause and you should look at this solution very carefully. So this is how we are going for the first part of applications of partial derivative. I hope all of you understand these four major sections of partial derivatives application. Later on we are going to extend the same idea for optimization and constraint optimization. Thank you.
Institute of Engineering and Technology.